In this video, I wanted to actually solve some street routing problems, basically go from start to finish and solve a complete problem. And basically, we've done a lot of videos, and I know there's been a lot of information, but each one of those kind of builds upon itself to describe, well, how do we actually solve these problems, what math goes into it, and why. But now let's actually do them and talk about how we solve a problem. And just to recap, from the past video, I talked about Eulerizing a graph, and to just remind you about that definition, we always can Eulerize a graph by connecting all the pairs of odd vertices together. So basically connect odd vertices together with new edges that should Eulerize the graph. And all that means is making it completely even. Because when we're looking at a graph, this was a problem that we encounter with a lot of street routing problems is, okay, this graph has some odd vertices. If I want to actually find an Euler circuit, I cannot do such because there are too many odds, right? Like looking at this one, it has two odd vertices here and here. So an Euler circuit would not exist. And if we're going to be Eulerizing a graph, the goal would be to find an Euler circuit, to which we can't. But basically, if we just were to add an additional edge between those two odds, that would Eulerize a graph, right? Because each of those two would change from degree 3 to degree 4. Now, it's an Euler, the graph has an Euler circuit because every vertex is odd. And once the graph has been Eulerized, which it now has been, we can find an Euler circuit by using Flory's algorithm. So we choose a starting point. Let's just say that we're choosing to start at vertex D here. And we travel along the edges of our choosing without deadheading. And basically, again, then from there, you can basically choose wherever you want. But you can understand why it's important to Eulerize first and understand Euler's path and circuit theorems, because if you don't, you're going to be completely lost in terms of how to actually do these problems. But it is relatively straightforward after all of that, because it comes down to where are the odd vertices, and then we can connect them together to make it so that we can solve it. And anyways, notice that it works out. And there we'd have an Euler circuit. Now, technically, the original graph did not have an Euler circuit, but that's what Eulerizing is all about. It's kind of like we have a graph, we fix it via Eulerization, then we solve. Done, we have our optimal route. So say that we were a security guard and we were trying to patrol this neighborhood, we now have an optimal route for going about finding it. And if you're thinking about, well, why am I adding an additional edge? Because I'm really changing the graph. But really what this additional edge would be the deadheading in the original example. And that's exactly what the video from our textbook or from our publisher was talking about. When we're adding additional edge, what does that mean? Basically, it's adding the edge to Eulerize the graph. When we've Eulerized it, we're encompassing the deadheading. So really, this 6 and 7, technically we're not traversing down two separate streets, but we're just traversing down the same street twice. And this green edge just was the minimum amount of deadheading necessary to actually complete the complete sweep of this graph. So it was not doable, but if we were to allow ourselves to deadhead specifically at those points, we'd be good to go. And so let's do a couple more examples. And I also wanted to practice the difference between Eulerizing and semi-Eulerizing, which was the difference between finding an Euler an Euler circuit and an Euler path. And in each case, we're going to start from G. So let's start with this one. And again, in these problems, we could imagine, say that we have a neighborhood here, and let's change up the problem. Let's say that we're delivering mail, and our goal is to deliver mail to across each of the lines. Let's say that we only have to deliver it on one side of the street, and we don't have to go down each street more than once, and we're able to do that. But you'll see from the homework that there's a question that gets into, well, what if we have to deliver mails to both sides of the street? How does that change the problem? But anyways, if we're thinking about trying to do a complete sweep of the neighborhood, again, we're thinking about Eulerization. We want to hit every edge that we have on our graph. And if you're wondering, well, what if there was an edge that I don't need? On your graph, you just would not make that an edge, because every edge on the graph represents a critical part of the graph to travel in the problem. And if the edge is not needed, we would disregard it from the graph, because that's what the graph is all about. What is the critical info? But anyways, step 1 is to find all the odd vertices, right? Because if I'm going to try to do find an Euler circuit here, I need to know, well, where are the odds? Well, and notice this graph has a ton of odds because we got some dead ends, which are degree 1, and we got some T intersections, which are all degree 3. So if we look at it, it has a total of, and actually notice that when I'm looking at this, there's instantly a problem I'm noticing is that I have 1, 2, 3, 4, 5, 6, 7. And if you remember Euler's sum of degree theorem, odd vertices always had to come in pairs. And if you were wondering when I was talking about Eulerizing here, how do I know that I can always pair them up? But basically, Euler also proved that they have to come in pairs, meaning you should always be able to Eulerize the graph. It's always going to be possible. And notice that really I just missed this vertex over here, which I'll pretend I did on purpose. But notice that there are 8. There should always be an even number of odds. There has to be by Euler's sum of degree theorem. And basically, what I want to do is pair them up one at a time in order to Eulerize the graph. So basically, if you're wondering, well, which one should I pair with which, you can use common sense. But I would try to pair all the vertices which are next to each other. Like, so I could pair these two. Well, those are dead ends. You know, the only way to get out of a dead end is to come back to where you were before. So those are kind of obvious solutions there for a deadheading. But notice that vertex I and G are across like that. And you might be wondering, well, can I connect them directly together like this? And this really depends on the context of the problem, because theoretically, yes, we could connect any 2 dots together with a line. But the problem in a street routing problem is that each edge represents a pre-existing street. And if I was thinking about this as like a neighborhood with a bunch of houses here, we could not drive across all the houses, right? And so this edge is not necessarily an option in a street routing problem. Whereas in other problems, a general Euler circuit, this would be a fine connection, no problem. But you know, this is something where your homework will ask you to Eulerize, and that's not going to be an acceptable option, depending. Where technically in my mind it is, but really how we could also do it is, obviously if we're trying to get in between those 2 points and connect them together, we have to use pre-existing roads. So we could kind of link them together like that. And notice that technically this is not connecting them directly together, but kind of routing them through another vertex. And even though this is also Eulerizing, because notice that this vertex started off as degree 3, it's now 4. This one's now 4 too. So those have both been made even. And since I use this one twice, this one actually retains its evenness. So we'd say that this graph is optimally Eulerized because each of the evens was connected. And again, you might be wondering, well, technically it was more optimal to do it like this, but in a real problem, that's not necessarily an option. And I don't really care about the distinction when it comes to the test, if you're wondering which is the right answer. Both are. It's just contextual. Anyways, then once it's been Eulerized, now we're not done because we also want to solve the problem. So we said that we wanted to find an Euler circuit starting from G. Now that the graph is Eulerized, we are able to find it. And again, you would not want to try to find it first because you're probably not going to do it properly without Eulerizing it. But now that it's been Eulerized, I'm just going to try to use every single edge that I have, and it should just work. So let's say I'm going to go north first. 1, 2, 3. And basically, I'm trying to find my Euler circuit. And notice each of the dead ends is now fixed because I don't get stuck, right? Because that's what all of those additional lines I added represented. And I mean, that's kind of obvious at the end of the day, right? You got to go down the dead end and come back. But notice at this point, there's another point that we can see as a problem. And since I started here at G, you know, I'm going to try to hit every edge. So again, when you're faced with choice, it doesn't necessarily matter where you go, but I'm just going to kind of choose randomly and say, well, notice that we are getting back to G here. Again, we haven't finished our Euler circuit because we need to hit every edge, and I have not hit these ones yet. So I can kind of go down this way, 15, 16, and come back like that. And that's kind of why I was saying in the previous video that Fleury's algorithm is not that useful. Because it does tell us like what to do, but really in terms of actually solving it and doing what I'm explaining in these problems, it says to travel along the edges of your choosing. It's not very helpful in actually determining the step-by-step nature. But basically, I would just practice this a few times and see if you can figure them out on your own. And on the next page, there is a group activity with a slightly harder problem that usually in class I would give you this as a, try it yourself, see if you can figure out the Eulerization. And usually test questions end up being something very similar to this after all is said and done. And in the next video, we'll do the same example, but we'll semi-Eulerize it instead.